Yes, hello and good morning. My name is Vidstrand. I work at the Research and Safety Assessment Department at SKB in Stockholm. My employment or title is Expert in Hydrogeology, so I have kind of the same background as Manu here, Mantreto, who gave a previous talk. My responsibility at SKB is mainly two-divided. I'm responsible for developing and user support of a numerical groundwater tool that we have, which models groundwater flow, but it also models chemical transport as long as it's not reactive chemistry. So we can mix species and we can move species, but we can't react them. We can also do temperature modeling and mechanical modeling in this tool. The other half is doing kind of relevant research to be able to better predict the safety long term for our repositories. And that relates then to different topics like us and Mano and previous presenters has talked about, that is geology, hydrogeology, chemistry and mechanics. And so it's a very integrated work. My speciality is in climate-driven hydrogeology. So what I've been working on the last 20 years of my life is how hydrogeology is affected in the future when we have permafrost in Sweden again, and we could have ice age coming with massive amounts of ice sitting on top of here. Up to 2 or even 3.5 kilometers of ice might cover Sweden again in the future. And this has really hard impacts on the system. I tried to make a presentation because I was asked to give a presentation where I show how we do safety assessment using these geoscientific models that us and Mano and Teresita should have talked about concerning chemistry. And I was trying to make a red path through the system here, let's this be the red path here. So, and that path is kind of a radionuclides path. The way a possible release from a deposition hole here or canister go through the geosphere into the biosphere and then out, and in the end expose the nature, human, animal and plants. So I just wanted to ask you, how many of you has a background in natural science? 3? Okay. And that's 2 geologists, or and yours? Sorry? Physicist. Physicist. Okay. Okay, and the rest of you is basically new to geology and chemistry and everything? Yeah. That's excellent. Okay.
What a good material to refer.
Yes. So, this is my content of a presentation and the title as it's given in the schedule. So I will talk a little bit about the repository, the site and the timescale that we are working on. This is kind of general things, and you have seen all of this before, so I will be rather quick there. I will also say a little bit of a construction and operation period. It's also a very quick period, and you maybe have heard a little bit of that earlier. The resaturation period, which I called it. These 2 periods are very important for the system, and they do impose lots of changes in the system on hydrogeology and especially on chemistry, I would say, and mechanical issues. But from the point of a radionuclides path, everything in these times is going into the repository and is pumped out. So we don't really need to understand how things move within the geosphere. We only need to understand how to treat it when we are exposed to it in like water that we need to pump out. A little bit of safety assessment scenarios, the release. I think Lena, my colleague, talked to you on Monday about the release a little bit. geoscientific models and introducing the path. And then I will focus on the geosphere, which we call it. We divide that in near the canister, near the deposition hole, transport in deformation zones, and in the end we have transport in the soil layers or regolith layers. I will basically say very little about the exposure and surface transport, but it's important to mention that in the end. So SKB system, you've seen this before. The main thing that we talk about and the long-term safety is this deep repository, the KBS3, which we call it in Sweden, in which we will store the spent fuel. But we have other types of repositories which we also need to do safety assessments for. We have an ongoing storage in outside Forsmark already, which is for low and intermediate waste that we have. It comes from medicine, industrial, so we handle that, and we need to do safety assessments for these two. But the main thing is this that I would talk about. The suggested site, you've seen it quite a lot. I'm not sure you've seen this picture. It's a photo from above. This is the Forsmark nuclear power plant, and the planned area for the repository. It's actually a suggested site. SKB suggested that in the applications that Assen talked about that we handled in 2011. And the authorities are the ones that decide if we are going to build it there or not. We believe that to be a very good site and hope that they say yes, but it's down to lots of people to decide. Yes?
Personally, do you think it's likely that it would be accepted?
Yes. If I have just a personal opinion, I think it's likely, because it is a really good site. But actually, statistically, it's almost impossible, because I think it's like 5 different levels of authorities in Sweden that has to say yes. And doing that as a chain, that is really suggesting a no. But I think it's a very good site. Sweden has for a long time been leading in this line, but now both French and Finland is ahead of us, and if they got a yes, I think it's very likely that we will also get a yes. So I hope Mano yesterday, when he talked about basic hydrology, talked about the input. The input of water is from the surface. We have rains, we have streams, we have the Baltic Sea. As you can see, this site is rather flat. It's lots of wetlands areas, and it's very coastal as of now. All these things govern the available system. Even if we talk about the fractures and things like that lead the water, my former mentor, the professor I had at Chalmers, he used to say that we have not more water than God gives, and God gives the water from above. If you believe in God or not, that's a different story, but it's true that the water comes from above. The timeline, I did this plot in linear scale. Actually, there's a lots of things happening here at 0, but the time we need to be safe is 1 million years. That is basically a political decision. For the low and intermediate repository, we only need to be safe for 100,000 years. That's also a political decision. Of course, it has some kind of relevance back to how long these radionuclides can be dangerous. But basically, someone says to SKB that you need to prove that your repository is safe for 1 million years. So, a little bit about construction and operation phases. Changing the time scale to logarithmic scale, the construction and operation is basically 100 years. We haven't started constructed yet. We don't know when. Hopefully something like in 4 or 5 years. If not, our time plan is going to go to hell. But in 4 or 5 years, we hope that we are able to start constructing. That will be about 5 or 6 years before we are done. And then we basically can start after 10 years to construct possible locations for storing these canisters. So we suggested design, at least I saw that Mano had this area. This is how it's supposed to look in the future. You have this Forsmark nuclear power plant here, so maybe you can remember the aerial photo. It was coming from somewhere here, looking downwards. We are going to construct like a big hole. It's ramp down and then a huge tunnel system. This is on many kilometer scale, so it's a really huge site. Looking down into one of these, there is going to be these deposition tunnels, and in deposition tunnels we are going to have deposition holes, and in each deposition hole there is going to be stored this canister containing the spent fuel. There's going to, oh sorry, approximately 7,000 of this canister is planned to the Forsmark site. So we will have potentially 7,000 leakage points, areas where we can have a loss of radionuclides to the system. And as I said, from somewhere here we are starting to deposit things, and from that time of course something can leak out into the system, but during this time the leakage will come into the tunnel and be pumped out. Two model results I will show here. This is showing how the water table at the surface is affected by this construction here. So basically you can see a pattern of these deformation zones that both us and Manu talked about. So we have to apply to environmental court, and they are most interested in which areas of the surface is affected. So even if we affect much more at deeper levels, the main interest is what do we affect at the surface. Like if we have a wetland there, you have special frogs or special flowers. We don't want them to be extinct or changed or having a new habitat due to our activities. So we have to apply for that with change. And the effect we see is very local. However, this is model results, and model results are always based on some kind of assumptions. So this is just one possible future. And the same model, if we are looking at the drawdown or the pressure change at 50 meters depth, you see now that the effect is much bigger. And the biggest effect is close here, and this shows basically that all water here is flowing towards the tunnel and out from the tunnel. It always flows from high pressure to low pressure. I'm sure Manu talked about that yesterday. So this is kind of a proof that we only need to care about the water we pump out during this time. After that we come into the resaturation phase, because what we are going to do is all these tunnel systems are going to be backfilled with bentonite. We have bentonite around the canisters, we have bentonite in the tunnels. At the end of each tunnel we will construct a plug of very high quality concrete structures. It's extremely high technology to construct this, and actually when they're doing these plugs they're using freezing in order to have it shrink and then expand so you really seal to the rock. It's really intriguing to follow that. And you will continue filling up that system And then in the end, the entire system is backfilled with this bentonite system, isolated with these plugs. And as Manu said, these are all given certain criteria for how permeable or how easy it is it is allowed for water to flow through them. But however, when we fill the repository, these materials are dry. And clay that is dry is basically sucking water, and it's sucking water with enormous powers. It's like 100 megapascal negative pressure. And that is going on for a long time. So basically the saturation time starts when we start to fill the system and acts for something like 1,000 to 4,000 or 5,000 years into the future. And still under all these times, all the water is going towards the tunnel system. So any leakage from the system into the geospheres can basically only start after somewhere at this point here. And then we have this radionuclear path into the geosphere system. Okay, any questions so far? So, a little bit of safety assessment scenarios, the release, talk about models and the path. So, you've probably seen this, and maybe some of you have a detailed knowledge about this. The fuel, when it's fresh, is like these cuts, and you can actually hold them in the hand. They're not really dangerous. They are stocked together in these cladding tubes, which are put in together to these assemblies of fuel. We put them into the reactors, take up the energy we want, about 4% or something like that. I don't know in details, but very little. And after that, we put these assemblies into the copper canister, and the fuel is looking like that, and it's very dangerous. And this is what we need to handle. Scenario analysis, I think Asen started to mention a little bit about that. We need to think out, think up, construct, whatever, all possible things that can happen to this canister in the future. We can have meteoric impacts. Someone has to calculate the likelihood for a meteor to hit the area and affect the system. One of the big effects of that is probably an earthquake. We can have earthquake just due to geological, tectonical issues, or we can have earthquakes due to ice age issues, loads of a big ice sheet. We can have changes in the system due to the ice. We have meltwater coming down, we have new loads. The climate could also change into some kind of very dry. Maybe not so likely for Sweden, but for other countries that could be a real reality. And for the US sites, some of the sites are really problematic due to these desert conditions and very low groundwaters. Yes, and lots of things that you can't really think about, not at least human intrusions. We may in the future forget about this repository and actually drill for energy and become exposed. The climate scenarios is basically what's driving most of the things we are doing. It is impossible to predict the future. We can't do that. We don't have models enough to do that. We don't understand the processes enough to do that. And hence we can't really focus on one most likely. Hence we need to construct a lot of different scenarios. And the climate scenarios that we construct are basically based on problems, issues that we want to look at. For instance, if we have this deep geological storage for the used fuel, it's planned at 500 meters depth. It's really critical that that repository is not become frozen. So one big question here can be, can a future climate when we have permafrost actually create conditions where the permafrost can go down to 500 meters depth? So we construct climate scenarios that would create really cold climate and the potential of freezing down to that. And can we really create that? And actually the answer is no. How much critical things we try, we can't get the permafrost down to 500 meters, which is good. Another critical question is, how large can this hydrostatic pressure become? If we have 3.5 kilometers of wet ice above us, then we have 3.5 kilometers of more water pressure forcing towards this copper canister. And if you have air in there, then you could actually implode the canister and get a failure of the system. Most of the problem we are working with is dilute waters. We can have dilute glacial meltwaters. The water melting underneath the ice sheets are very dilute. That means that they are very fresh and often very rich of oxygen. But actually, even the rain we have today is very dilute. So if it continues to rain for a long time, like 50,000 years or something like that, that will also affect the integrity of the system. If the water is dilute during a long time, this bentonite barrier, which actually starts to become more like a fluid than a bentonite, like a clay. And when it's fluid, and if you have a flow through it, it can erode. The water takes the clay away through the fracture system, and then it just disappears. And what can happen after that is that then the water is actually exposing the copper canister directly, and it can corrode, and then the fuel is open to exposure. We could have other climate scenarios for this low and intermediate short-lived waste storage. It's only 60 meters below the ground, so we know for sure that sometimes in the future it will freeze. So then the question is not, can it freeze? The question is, when, as earliest, can it freeze? So then you have to create climate scenarios trying to understand when can it freeze as earliest. And all these constructed climate scenarios are the basis for these safety assessments that we are doing. And below here I have the references to at least relevant papers or reports for most of the things that I think that you may want to look at. If it's scientific papers, you have to pay for them, I guess, but you can always download them from the web. All SKB's report is, as Hassan said, free on our webpage. You can download them. So it's just to go find them. So climate scenarios related to hydrogeology. We have something called temperate conditions. That is like today, present day conditions. We have positive annual mean temperatures, so we have no permafrost in the system. We have a periglacial climate condition, and periglacial means actually that it's in front of an ice sheet. But basically what we mean is that we have permafrost in the system. The permafrost can be completely cover everything, or it could be holes in the permafrost, which is often occurring where you have lakes or ponds or rivers. So we can have different kinds of permafrost. The climate could be wet or dry, and that has different impact on the hydraulics. Then we have basically three kinds of possible situations where we have ice sheets. We have something called a glacial domain, and glacial domain is actually beneath the ice. So how is the hydraulic acting under the ice? But the most critical ones we have is this glacial advance, where the ice sheet is, or the ice sheet's margin is moving forward over the site, injecting water into the system as it goes. And we also has a retreating phase. For Forsmark, the retreat is occurring with water in front of it. We actually have a big sea. The last retreat we had about 12,000 years ago, the sea level was about 100 meters over the Forsmark site. And we could also have completely submerged conditions, right? We only have water. And actually, the most realistic future scenarios is that we will have an increase in sea levels for at least a couple of thousand years. So we will have land coverage by sea in Sweden again for a while. So no expensive shore housings is recommended, at least if you plan for having houses in 100 years time, something like that. So don't buy for your grandchildren. So what can this construct? Basically, I've said it before, we have this dilution of a buffer, we can have freezing of barriers, dilution and erosion. Erosion occurs when we have high flows. And we have failure scenarios, which is basically down to earthquakes and corrosion. That is the things that can make the copper canister break, and we can have a release of a radionuclides to the system. This slide I took from Lena's presentation, which was on Monday, I think. And basically, if you have a break in the copper canister and the water going through the fuel, the spent fuel, it will pick up radionuclides, which will go into the eosphere, into a fracture system. And remember, the failures we have is earthquake, that we shear it off or we dilute and erode the bentonite. So if this happens, the bentonite just around the canister is not there anymore. So we have a direct input into the rock. So the safety assessment we are doing is assuming that the bentonite is disappeared and everything needs to be accounted for in the geosphere. So I will look now at the transport through the rock, and basically that is a path along a fracture system. Or if we look at it like this, we go to models. I think Manu said very well, Asan is too polite to say that, but the big mother of everything we do is geology. Being a hydrogeologist, I call myself hydrogeologist, meaning I use water to understand geology. We need to understand geology, otherwise we can't do anything. Geology is extremely complex, and we have was it like 50 boreholes in total? It's like 50 needles in a haystack. So we don't have very much information, and based on all this we need to say something. I think from a geological point of view, Asen is very pleased. We have good confidence that the models we have in geology is good. But from a hydrogeology point of view, it's not so good that we have few fractures down there, because the location of each fracture is extremely uncertain. So it can be everywhere. That means that we need to be able to predict lots of statistical models and lots of realizations and lots of uncertainties. And we do that by these models, cases, and realizations. So we have models that contains everything we are pretty certain of, which is basically the deformation zones. We can have uncertainties of those, but from a geometrical point of view, we are quite certain. But we can have variants. We can have a deformation zones goes like that, and then meet again. But it might affect something. So we can have cases, and we have property variants, which is cases. And then for each of these variants, we need a lot of realization, because we need to cover the uncertainties. Based on this geometrical model from geology, we assign properties. That is thermal properties, which we need in order to understand the thermal behavior. As Asen said, the fuel, when we put it down, is very warm and it continues to warm up for a couple of years before it starts to cool down. And that might affect the rock, it might crack the rock, it might expand the rock, and we might have new stresses to account for. And that affects mechanical properties. They might change due to thermal conditions. They might also change due to hydraulic conditions. And hydraulic condition might change due to mechanical conditions. And transport properties here. Am I moving away from the camera? Okay. I've not really said anything about chemistry and chemical properties, because to me chemical properties are not really existing. They are, however, a consequence of all this. So we have a chemical system which affects everything. There are, of course, chemical properties, but I don't really think we account for them in the way of model creating. So based on this, however, we create mechanical models, hydrogeological models, and chemical models. And they all need to work together. So we have this as a basis, and then all these three needs to talk the same language. If I have a certain hydrogeological model, it might not confirm the chemistry model. And if the chemistry turns out to be something else in my hydrogeological model when I'm using that, then the hydrogeological model is wrong. So we need to work all these models all the time together until they work together. And we need to have many variants that all works together. So it's lots of integration. This is done during extreme time pressure. Both us and Manu was involved in the site investigations, and I know that the time for integrating between the disciplines are very limited. You basically only have time to follow your own time schedule. But it's very critical that we do that, and we actually see in the end when we have missed something, because it's not fitting together. What we really want to do in the safety assessment is this transport models, and I will talk a little bit about what affects the transport models. But that is basically a result of all these three, and these three are the result of that. And the transport models leads to a release somewhere, and that create an ecosystem model where we have exposure and the dose calculations. I will basically not talk about that, but that is the things that we need to explain to the authorities, that the dose is acceptable. We need to have a dose that is below a certain value. So the radionuclide path is going to go somewhere from a release at a canister, through the rock into a deformation zone, and somewhere come up to the surface. So near deposition hole transport is the next thing I'm going to handle. Do you have any questions therefore up to now? Okay, back to this picture. I said that we have a release coming into the rock and it goes away in the fracture system. If we scale up this and use a different picture and follow these two particles, it could look like this. So the starting point was a fracture intersecting the canister, and that fracture is connected to a fracture network. Asen mentioned a little bit about that, and Manu talked about conductive fracture frequencies. All these fractures are a conductive fracture network. So water can flow through them. What they can do to start with is having an advective transport, and that is basically following this Darcy's law. So we have a pressure gradient driving these particles along the water flow in the fracture, and they follow basically the same path. That is advective transport, and that's the simple thing. That is something we learned in the 1800s by Dorsey law. And it works as long as we don't have extreme gradients. However, in the fracture system, we can have something which I chose to mention, have a notation of macro dispersion. That is, the particles can choose to have different ways. It can go that fracture, and it can go that fracture, and continue the system. That would mean that these two particles will have different ways to the surface. And it will most likely take different time for the particles to go to the surface. We can also have something called microdispersion. If you look at a single fracture plane, all these point oily iron oxidized bacteria somehow illustrating where water is flowing. So this area has actually no water. So in a single fracture plane, we don't have water everywhere. And if we conceptualize that as a picture, we have basically channels in the fracture. And this leads to the same behavior. The water takes different paths in the fracture, which is microdispersion. If we go into this single fracture channel in the fracture plane, it can actually look a little bit like this. And we can have the main fracture channel. It could connect to microporosity, microfractures entering into the thing we think of like intact rock, but it's actually full of fractures, small fractures sticking together. In the fractures we can have calcite, other mineral crystals, we could have broken rocks, and we have also a fringe zone of changed rock called myelonites. And all these things can affect the flow. So if we follow a particle for this, it can have this advective flow through the channel. But it can also have something which we call matrix diffusion. It can find its way into these microfractures. And basically it does that due to chemical differences. So it's diffused into the system because when it starts, it's here, but it's nothing here. So you have a chemical gradient wanting to feed into the system. The transport along here is due to pressure. It just follows the water, but this is due to chemical differences. It's kind of the same equations, but it's different physics. The particle can also find these things that it can get stuck to. It can sorb. And if it sorbs to the surface of something, it can be sorbed there for a very long time. It can sorb in the main fracture, but it can also sorb in here, on the walls or on other things that it goes to find there. So a couple of examples what this can do. If we only have an advective flow, it almost looks like a plug flow. The particle, everything will move with the same velocity through the fracture, and everything, if we look from a point here to here, if we release something here, everything will come out here at the same time. So we will have basically a peak of the solutes coming out. If we add dispersion, remember that it could take different paths. Some things will be quicker and something will be slower. So we'll have a spread around this main or average release time. If we have matrix diffusion, it actually means that some of the particles will take extremely long time. It will go into the system and stay there for a while, and then it will go out again. And if we add sorption, it will take even longer times. And you also notice that this peak here is going down because it's stuck and more and more. And this is positive for us because that stops the radionuclides from coming out as a concentrated force. If everything would come out as this peak, it would be an extremely high exposure when that comes. So, what do we need to do this near depositional near canister system, we need a fracture network. And that is an unknown reality. We will never be able to do that. We need to do statistical realizations. We need to do many of them. You can have different kind of statistics describing the same things, and that is actually the things that are affecting most. If you do lots of realization of the same things, of the same statistics, it will basically produce the same result. But if you have different variants, for instance, we can have models that cluster fractures. So if you see one fracture, it's more likely that you have lots of fracture close to that. A little bit like a deformation zone. We need to assign hydraulic properties to those and transport properties to those. And Manu talked yesterday about a relationship between size of fractures and transmissivity of these fractures. And that is something we have tried to find out through empirical information. We have looked at fractures that we have some kind of ideas how big they are and measure these transmissivities. And basically we have found that there is a size transmissivity relationship, so that a larger fracture is more likely to be more transmissive. And that goes all the way to the deformation zone. So a deformation zone which is many kilometers long is more likely to have a high transmissivity than a small fracture of 1 meter size or something like that. All this is affected by geological properties, which I said it here. It's kind of mineralogy. A biotite, for instance, is very prone of sorbing, while a quartz mineral has basically no sorption at all. The chemical situation affects all these properties. So if you have a dilute system, you have some kind of properties. If you have a very saline system, you have other properties. So when the system changes in time, all these properties change in time. And the same goes for the mechanical situation. If we have 3 kilometers of ice sitting on top of a system, a horizontal fracture is more likely to be squeezed together, and the less water is possible to transmit through it. So everything changes in time, and we need to understand that system. So not only integrating hydrogeology, mechanics, chemistry, we also need to understand climate and climate change. The deformation zone and its transport. I actually moved from Forsmark because I found a really good picture in an old report. It's from 2005. It's for the Laxima site. It was done during the site investigation phases. Here is the island of Espö. You haven't been there yet, but you're going there. Is it already tomorrow or after next week? And Oskarshamn is down here somewhere. Sorry, I don't know exactly where. All these kind of black line are deformation zones, or actually they are lineaments. So they are shown from, or visible from this kind of magnetic maps or aerial photos as topographical structures. But they are interpreted to contain a deformation zone. And some of them has been investigated, so we have properties on them. So adding transmissivities to these, then what's going to be shown in the next figure is that we released particles here everywhere. And this red line is the water divide, so that means that that is the highest elevation in the system. Out here you have the sea, which is the lowest pressure in the system, so water will flow from here to there. So what will happen if we release particles here? Actually, they will start to flow, and they flow until they hit the first deformation zone. And then they follow these deformation zones downstream. So when we define this near deposition hole, that's very important for the first time. But as soon as it hits a deformation zone, it's going to follow that zone. And basically it's out of our control, and we want to have, someone talked about respect distances, and basically we want to have respect distances due to this, but mostly we want to have it due to safety for earthquakes.
Just one question, out of curiosity.
Sorry?
How much time did that take for those particles in that situation to reach the sea? Just to have an idea.
I don't know that, but I will show you an example from another model. So, what is a deformation zone? Assen talked a lot about that. This is a photo of that, and this is a sketch. I don't know if you see that, but it's lots of small blue lines in here. So basically, the deformation zone is a set of lots of fractures. So all these near depositional processes which I talked about, the dispersion, the diffusion, everything is valid also in the deformation zone. So what do we need? We need the deformation zone geometry, and that is modeled, so it's not 100% certain, but I think it's really good. And the uncertainty of this is probably the least we have in our models. We need to assign hydrogeological properties to these. Again, these are very discrete features, so we can actually focus on them. We have drilled lots of boreholes focusing on hitting these deformation zones. So compared to the rock in between the deformation zones, we have lots of information. Still few, but lots, if you understand what I mean by that. So the hydrogeological properties of the deformation zones is also rather good. But as I talked about before, everything changes in time. The chemical situation, the mechanical situation, everything. Okay, transport times. So this is the example. This is back to Forsmark. This shows 5 specific points, 1, 2, 3, 4, 5, where 4 is sitting in the middle of a deformation zone. 1, 3, and 5 is sitting around the lens, close to deformation zones, and 2 is sitting in good rock, and you can see it here. It's actually in the dark blue, which is basically fracture-free rock. So if we look at the time it takes for these particles to leave, the line here represents the 7,000 positions available in here, and the colored dots here represent the 5 points. So the ones close to the deformation zones or in the deformation zones, they actually find it's from 500 meters depth to the surface in something like 60, 70 years, while it takes 300, 400 years for the particles leaving from this good one. So the good host rock close to the deformations, far away from the deformation zones, is very important for this time. So just a couple of quick words about the regolith layer transport. We haven't really focused on that. Both Assen and Mano talked about bedrock, and that is basically SKB's focus. But actually the research is heading towards the regoliths, because lots of the time delay is going to be up there. The problem is that it's very close to the exposure, so we can't really distinguish between this level. So what do we do in the quaternary geology, which we call it in Sweden, because all our regoliths are quaternary. Basically, I think we have maybe something in Skåne that's tertiary, but basic quaternary. Same as in bedrock geology, we create maps. So this is a map about what we see at surface, actually at half a meter's depth. So we have people employed going around measuring what's a half a meter down. Yes?
What is regolith?
Regolith, basically it's everything that you can dig in. So if you can dig, it's regolith. Soil is more a chemical meaning, but it's, do you call it soils? When you, okay. So we have different kinds of regolith here. It's peat, till, which is a very common thing in Sweden, actually the most common. We have clays. And you see here, everything here is below sea at the moment, and it's very rich of clays. So in future we will have lots of clay exposure there, but now it's beneath the sea. So based on this, we create models. We also have drilled through all the way down to the bedrock, so we can have a three-dimensional map of these regoliths, and this shows an example. This is from Forsmark, and it's close up just above this SFR, which is the low and intermediate repository. So you could actually see how we have the blue one here as the bedrock. We have a surface layer of the bedrock, which is weathered and highly fractured, and then we have till, the yellow thing here, and clay and different materials. The colors here shows conductivities for these materials in logarithmic scale. So red is 10 to the minus 4 about, and blue here is 10 to the minus 7. So we need that, same as everything else. And also, again, this is going to change in time. So the models. We have a model from geology, a model from mechanics, a model from chemistry, and lying a little bit lazy here on the side, we have my main model, the hydrogeological model. All these needs to talk together, and I think both Manu and Assen talked very well about that these actually speak together, which is a very good sign. So a little bit of transport properties. These are slides I took yesterday from Teresita's presentation, because I thought that I needed them to explain a little bit. So they are not really mine, so I apologize if I can't really explain everything in details. But basically what the chemistry do and hydrological parameters is that we have chemistry composition. So the water has different species. It can have different pH, EH, alkalinity, and all these compositions and chemical situation leads to different chemical reactions. And they also, the water react with the minerals. And all these create a chemistry situation that actually provides the transport properties we are looking at. So if anything here change, the transport property change. It might not be a big change, but if we have big change in the water chemistry, it could also be a big change in the properties, and we need to be able to account for that. For instance, if we go to these extreme glacial waters that we are thinking we will have in the future, the KD values are actually quite different. So we need to understand how to do that. The chemist people are doing chemical modeling and sorption modeling in order to give us these KD values. The KD values describe how things get stuck to materials, the sorption I talked about. And then that leads to transport properties, and we can do with transport model. Just a couple of confusing words about porosity. Porosity is, to me, the most confusing concept in the world. It's very clear what it is. It's the volume available, the free volume in a tight material. So if you fill a bath tube with ping pong balls, it's the air between the ping pong balls. But what it means, it's much more complicated. For bedrock, the total porosity is about 2%. Of these 2%, 0.2 to 1% typically is found in fractures. Not all of these fractures are connected. They could be isolated fractures, just a fracture sitting somewhere. But if a fracture is connected to something else, it's called the kinematic porosity. That's the porosity that actually allows flow. And as you see, the values here are much bigger than these ones. And actually these values are something we measure in the field by field experiment. It's actually the way we interpret the time it takes for something to go from point A to point B. But we have no idea about kinematic porosity, except for what I said. It's the connected system. Matrix porosity, that is everything that is not fractures. If we have grains, they are grown together, but in between them you could have pores or free space. And maybe these free spaces are actually connected through microfractures or microchannels. So on long time scales and on very slow processes, all these porosity might be very important. And it's actually very important when we talk about, for instance, the wetting of this bentonite that we talked about during the saturation phase, because most of the water is going to come from the matrix. As you see, 1.8 of 2, that is most of the water. So when we say that most of the water is in the fractures, it's not really true. Most of the water are in the matrix. But that's water we never see. The water we see is basically this, which is a tiny bit. Effective diffusivity, when we have very little advective flow, the transport is through these chemical gradients. So if we have a rock sample and we have a species on one side and nothing on the other side, that species want to go through the rock due to this chemical gradient. So it starts to diffuse. So it's the same kind of process, but it's driven by something else. And the speed basically by which it does that is describing this effective diffusivity. We have a diffusivity if we pour species into free water. That's a free diffusivity. The thing we measure here is a combination of this free water tortuosity, which is how the particles go through the porous media like this, for instance. And it could also be that some paths on this way getting very narrow. And if you have a big species, it won't go through that channel, so it has to go somewhere else. So that kind of restricts this possibility of diffusion. And then we also add the total porosity into this term. And that creates the effective diffusivity, which goes into our equations and models. The KD, you can look at this in details and look at reference, but the important thing is to remember this. And it's also a little bit confusing. And what it is the mass of species that is stuck to the materials. So it's not the mass of the material, it's the mass of species stuck to the material, divided by the mass of species that are free in the solution. That is something we can measure in laboratories. It's easy for soils, and that's kind of often done in remediation problems and remediated projects. For rock, it's a really hard processes, and we're actually doing it as good as we can by crushing the rock into small pieces and then leak out the things that was stuck to the material. So it's time-consuming and very expensive, and I think in Sweden we send everything to Switzerland to do that. So it's very few people that does it, and it's a very uncertain method, but that's what we can do at the moment. So the time for potential transport away from repository, as I said, and this is something we need to account for. This is present day of Forsmark. This, if you remember, is the shape of the model I showed in the beginning of the drawdown of the water table. This is how it looks today. This is land. All this is sea at the moment. And the site is here about. If you remember the image I had about the soil model, that was the strange thing on the top there, which was it's a pier, so it's a fill material. If we look at the release, from a model from this deep repository. Here you have this strange thing which I called about the piers. You can see all the release particles of today from the repository is coming as these red dots. They follow two things. They follow basically the shoreline, which you might see in this weak greenish color down here. This is possible to see it. Also in the back. You have to look in details of the things. But it also follows the deformation zones. So see how important the deformation zone model is. However, this, as I said, is the landscape of today. This is how the shoreline looks. This is how it's going to be in the future. Moving 500 years into the future. Further 500 years. 1,000 more years. 1,000 more years. And 1,000 more years. So 4,000 years into the future, Forsmark is going to look like this. And this, that was very coastal now, is far away from the sea. This is actually still sea, but just for a couple of more years. Then it's starting to be a really small lake. So this is going to change. It's going to change the chemistry, it's going to change lots of things, but it's also going to change the discharge locations. So this is released from different times, and you saw before the 2000, which is here the green dots. If we go into the future, and far into the future, particles will go down to the new shoreline here. So when we look at the release of particles, we need to account for the change in the future and the change of the system.
So actually, particles will almost do those like fracture zones into the rock to the coastline. I mean, even if you move the coastline.
Yes, the coastline is the most controlling thing. But most of its particles actually go along these deformation zones all the way to the coast. So it goes to the coast and then up. Yes?
What kind of model and factors did you use to predict the change in landscape? Like SH262V?
These models?
Yeah.
But there are basically climate and isostatic models to show the change of the sea. So that is kind of pure physics. But of course it's interpretation of large-scale models, because we don't really know what's affecting the ice sheet on Greenland and things like that. But it's kind of well documented, and scientists agree on this. The development here, you see that we get some of it, maybe we can go, you see like here, these lakes are becoming smaller and filled with peat, and that kind of based on models that they do at Umeå University, which I'm not really into, but they model how a lake grows when it's filled with materials and it disappears with time. So it's based on two different modeling approaches, one for the sea level and one for filling up lakes and river systems. We also have these big changes of the climate. So if we have a system like this today and release from particles here and the discharge controlled by present day topography, how will it look like in this system? So this is coming from another model. This is how it looks today. As you can see, the red dots here are illustrating a few of the particles discharging close to the shoreline and deformation zones. The blue is where they start. So a particle that rains here will end up to a deposition hole and then continue and become a red one. When we have the ice sheet moving in, so this picture here in whitish color is representing the ice. The ice margin is here, And if you can see, I think it says 900 there. That's the thickness of ice sheet at that elevation, at that distance from the margin. So it's increased rapidly. The area in front of here is frozen with permafrost, and only these blue dots are open. They are small lakes. And maybe you can't really see them, but all these reds are now found in basically these three here, except for 2%, which comes up here, which are deformation zones in the permafrost. And all the blue ones that came here are now stuck on the border here. So they actually came from somewhere here, far away up in the mountain range. So the system is changing rapidly, both on near time and also on long times. We don't expect the future ice age in Forsmark for at least 50,000 years. So if you remember, I said we had 7,000 potential deposition hole canister locations. If we look at the velocities, at groundwater velocities at these positions for different climates. So this is the temperate case, like today. This is the mean value. This is the minimum value, and that's the maximum values that these canisters have. And if we have permafrost on top instead of present day conditions, all these becomes a little bit lower. If we have water, they become even lower because we take away the driving force. If we have a flat sea on top of that, there is no pressure gradient. It's just standing there. But if we have this ice coming into the system, so glacial case with permafrost, that is when the ice comes in and stands just above a repository. We actually have an increase by about 2 orders of magnitude. So that is going to lead to this erosion problem when the bentonite is flushed out if it's dilute enough, which is most likely is going to be because this water is very dilute. And this is the flow when the ice is as thickest, and I think it was 2.7 kilometers in this scenario, something like that. And it's actually a little bit lower than it is today, but very close. And that is because the ice has a slow slope always towards the front. Okay, so we have looked at the particles moving from this point to that point. And that kind of was the main talk for me. I'm close to the end now. But I will show the effect of this radionuclide transport, and I will show a little bit of a biosphere. So if we look at this case where the bentonite is diluted, eroded, and then corroded capsules, so we have a release. And we look at these capsules because these are the capsules that contain the highest flow. And we subject them to a transient climate, which is temperate, like today, periglacial, permafrost, temperate, permafrost, ice comes in, maximum, ice goes away, beneath sea, frozen again, permafrost, and new ice age. That is basically the last ice age we had in Sweden. So this is the Weichsel glaciation. I'm not sure you talked about that in the geological sessions, but most likely you did. So if we look at all particles leaving from these positions, today they all would come up in this red dot. But if we account for this climate sequence and has a continuous release from 40,000 and into the future, they will come up in this volume. So the climate change affects the release locations, and of course it changes also the length that the particles appear in the system. And these are actually plots of the exposure in becquerels per year, so it's kind of showing. And it's rather interesting because it's not so much difference in looking at everything coming out here or coming out here. So it's the same, red and green. So the maximum exposure is about the same, but, and that is also good because doing it this transient way is much more complex and time consuming and computer consuming. So what will happen when it comes out? It will come out here as a discharge into some kind of biosphere object. Lots of things will happen there, and in the end maybe a person will eat the fish that has got a little bit of this discharge into it. We also can have an influx. That influx could be of fresh water, and then it dilutes this thing, but it could also be from an upstream release. So it could also contain nuclides. So nuclides can come from here and here. And it can also disappear downstream to the next system. So you need to account for a series of different systems. And this system also, as we talked about, change in time. So what's a lake now will be a lake of mire in the future, and in the end it's a peat bog, and soon after a peat bog it's going to be a perfect agricultural land, so people will start to farm here. And if we have had lots of release here and there are lots of particles in these sediment, the plants we are growing here will accumulate those. So we can also have this potential release into this system, and this is how they do those calculations. They account for all these different effects. I won't go into that in details, but so a couple of final words. The transport, I think, is affected by lots of processes. We have this dispersion, which could spread it away along different paths. We have diffusion, where it goes into the matrix. We have sorption, where it gets stuck to things. And all these delay the release, which are good because we need to delay it as long as possible. So actually we want to find a site that has good sorbing capacity or good diffusion capacity. The models we are using, the scientific models, they need to talk together and they need to fit together. If they don't fit together, something is wrong and we need to restart all over again. And by that, I would like to end with a picture of my favorite Swedish photographer, Erik Johansson. If you haven't looked at him before, please do so. He has lots of things. I typically use this because I think it's an excellent show of how we are paving the road for the future peoples. Thank you very much.
So you have Einstein, you have Erik Johansson also. Now questions, please.